From classical electrodynamics, we know that opposite charges attract while like charges repel one another. In an atom, there exist positive protons and negative electrons. It would make sense that the electrons would be interspersed by protons, like plum pudding. But we know the atom has a nucleus, so why would the protons be held together if they repel each other? Let's look at two protons 1 femtometer apart. We know there is electrostatic repulsion from their like charges, and it can be calculated from Coulomb's law. There is also the attractive gravitational force from classical mechanics, which is calculated with the law of universal gravitation. But we find the repulsive force is 36 orders of magnitude greater than the attractive one. There must be something else to keep the nucleus together. Let's take a look at the substructure of protons. Nucleons, aka protons and neutrons, are made of quarks. Quarks are thought to be a fundamental particle, meaning they have no smaller components. There are 6 types of quarks known as flavors, but only 2 flavors compose nucleons, the up and down quarks. Up quarks are symbolized with a U, and down quarks with a D. Up quarks have a charge of positive 2/3 e, and down have one of negative 1/3 e. Like all particles, quarks have corresponding antiparticles, antiquarks. So there is the anti-up quark with a charge of negative 2/3 e, and the anti-down quark with a charge of positive 1/3 e. Protons are made of 2 up quarks and 1 down quark, while neutrons are made of 1 up quark and 2 down quarks. Quarks never exist on their own, always bound to one another in baryons or mesons. Baryons have an odd number of quarks, like protons and neutrons. Mesons exist as quark-antiquark pairs. Nucleons can emit mesons, including the pi meson or pion. The pion acts as a force carrier between the particles, binding them together through an exchange of energy and momentum. The positive and negative pions have a mean lifetime of about 26 nanoseconds, while the neutral pion has a mean lifetime of 84 attoseconds. Let's look at the nuclear interaction between 2 protons. One proton emits a neutral pion, and it is absorbed by the other. Note that the net amount of each quark stays the same. But protons are not only bound to one another, they are also attracted to the neutrons. One proton emits a quark-antiquark pair. The proton and the pair become a neutron and a positive pion. The neutron absorbs the positive pion, then the neutron becomes a proton, and the remaining quark-antiquark pair decays. Let's get back to the 2 protons. The nuclear force has no simple equation to represent it, but at 1 femtometer, it is around 25,000 newtons. So the nuclear force is literally what keeps us all together.